So the next chi-square video goes over goodness of fit tests. So we'll go over the formal procedure, and before we go over the formal procedure, we'll break down the procedure step by step. And it's going to be 4 steps, A through D. We'll talk about the actual procedure itself and a bit of an outline for it, and then we'll go ahead and run a full one with no guidance of like a parts A, B, C, D. So we'll just following the actual 4-step procedure to the best of our ability on that one. So only 2 problems on this one. So we'll go straight to number 1. So this thing reads, according to U.S. Census data, the U.S. population had the following household type distribution shown in the table below. I don't remember exactly what year this was, whether this was 2000 or 2010. Obviously the 2020 one's not finished yet, so it's either 2000 or 2010. I don't remember exactly which one it was, and I should have put it in there. But this is actual census data, or based off of actual census data. And type of household. We see 1, 2, 3, 4, 5 categories. 5 categories that they chose to show. That's more categories than that if you wanted to be more specific. First category, married with children. Married with no children. Second category, single parent. 1-person households. And then there's others. Other situation. So these are just percentages. Let's see. If we continue, the following results are based on a random sample of the community from Dove Creek, Montana. So data for a specific city. So just one particular city. And here we have the breakdown by household type. Same types. Married with kids, there's 102. Married no kids, 112 households. Single parent, 33. 1-person, 96. And then other, 68. So letter A. State a set of hypotheses for testing whether or not the distribution of types of households in Dove Creek, Montana fits that for the entire population of U.S. households. So we're not talking about 2 different populations. We have one population distribution. So this is the major distribution that we're going to be checking against. And then we have an individual sample. So one sample, and that's from Dove Creek, Montana. So we only have one sample. We don't have 2 samples that we're comparing. It's one sample and checking to see if it fits this larger distribution or this distribution that's assumed to be the case for a certain group of people, whatever. So hypotheses are, or the hypothesis is, that's the null hypothesis, that is, that the Dove Creek, Montana distribution household distribution looks like the one for the rest of the United States, or for all of the United States. So then that's my null hypothesis. And the way that we normally do this isn't done qualitatively, this is done numerically. So we give actual proportions in this case. So there are 5 categories, so we're going to have 5 proportions, all of which must add up to. So collectively, those 5 proportions must add up to 1, or 100% if you're talking about a percentage. So we'll talk about the first proportion. So P for married with kids. So I'm going to use that scheme. And that's supposed to equal to, and I zoomed in too much, 0.26. The proportion of those married with no kids, so no kids, is equal to 0.29. Then we have 3 more categories. Single parent, so the proportion of the single parent households, 0.099%. Proportion for 1-person households, or single parent households, and versus 1 parent or 1-person household. That's going to look a little different if it's SP and then OP. I'll leave it that way either way. So 0.25%, and then the proportion for other category, so just O, is equal to 0.11. And I put percentage on the 0.25. That shouldn't have been a percentage. These are proportions, not percentages. So there's my null hypothesis. Those are the claimed proportions per category, and there's 5 categories. So I'm going to write that on the side. 5 categories. Alternative hypothesis. So the alternative hypothesis is the situation where one of these, at least one of these, significantly differs from what's expected. So one of these 5 proportions, I'll go ahead and say, at least. So at least one, I was supposed to write of these proportions is significantly different. Let's say just different is different for Dove Creek, Montana. And Montana, I don't remember what I think it's MT, the abbreviation. So I'm being lazy, I could just write out the word Montana, but the abbreviation I believe is MT. So those are our two hypotheses. So either these proportions apply for Dove Creek, Montana, or one of those is off a little bit, or at least off by a little bit. So those are our two hypotheses. We can move on to the next part, Part B. Check conditions for using a chi-square goodness of fit test. So there are two conditions. The two conditions, either a random sample was taken or some sort of a random process is being employed some way, somehow. So in this case, if I look back up here, the following results are based on a random sample of the community of Dove Creek, Montana. So this is a random sample. Random sample given. The second condition deals with expected counts. Now I'm already looking, and in order for me to calculate expected counts, I'm going to need a total. And they didn't give us a total because, well, that was me. I'm the one that wrote this, so I'm the one that didn't write a total in there. So I think the reason why I did that, sometimes on the AP exam, multiple choice especially, they'll be jerks about it and they won't give you a total. So you'll have to actually calculate the total yourself if you're having to calculate something like an expected count, or if you remember going back to contingency tables, two-way tables, having to calculate probabilities based off of two-way tables, they won't give you the total sometimes and you'll have to calculate them yourself. So I think I did that on purpose just so I would actually have to spend time finding out that total. So at this point, I'll go ahead and just get a calculator. And the calculator result is 411. So then what we do is, I don't think I want to calculate percentages. We want what we call expected counts. So I'm going to give the expected counts. And there's several ways you can get away with satisfying the expected count condition. So the idea is the expected counts need to be large, and expected counts need to be at least 5. So what you do is you can give, or you can calculate all of them, not show the work for any of them, and then just go ahead and show the work for the smallest one. And then you claim that that's the smallest one, it's greater than or equal to 5, and so we're good. So check mark on that condition. Another thing, which I consider the most safe, is to actually draw a table. Either extend the table that's already given, or you just give the table here. And I'll go ahead and do that. So for the married with kids, the first category, expected count, there was 411. We were expecting 26% to fit in that category according to the US distribution, so 0.26 times 411. So 0.26 times 411, and the expected value is 106.86. Next one. 29% should have married couples with no kids. So out of the 411 times 0.29, we were expecting 119.19 households out of the 411 to be under the category married with no kids. Single parent households, 9% in the US, so 0.09 times 411. So we were expecting 36.99 single parent households, and we got 33, so it's kind of close. One person homes, 96 out of the 411, which that 96 should have been 25% out of the 411, 102.75. So 102.75, and then we have one last category, other, 11%, so 0.11 times 411, and we were expecting 45.21. So I'm going to go ahead and box these, make it look like a table, and I'll title it expected counts. So then here, all expected counts shown in the table are large enough. What is large enough? We'd already stated, at least 5. So then I'll go ahead and point to that and put a check mark on that. Random sample given, I forgot to check mark that one. And those are our only 2 conditions for using a chi-square goodness of fit test. So moving on to letter C. Now we calculate. So the same 4 steps: hypotheses first, or you name the estimator to, or the parameter to be estimated. Then you check conditions, you name the test, and then or the procedure, and then you check conditions for applying that procedure. Third step is you run your calculations. So letter C is where we're going to run the calculations. Letter D is where we conclude our test and interpret results, all that good stuff. So for letter C, chi-square statistic, if you remember, it's equal to the sum. Let me write a better sigma, because that sigma was crap. So it's sigma observed minus expected. We square this difference and we divide by the expected. And we do that for each of the 5 categories. So that's going to equal to, in this case, not 106 yet. What was the observed one? Observed's 102 minus 106.86. Let me go ahead and fast forward to having this written all in already. Okay, so that's what that looks like all filled in. Those are for all 5 categories. So it's a sum, because there's 5 categories. 1, 2, 3, 4, 5. So what you're doing is you're carrying out that formula for each category and then adding the results. So then I'm going to have to type this into a calculator. And so that way I don't bore you with this, I'll also skip ahead to the result on that one too. So this ends up being 13.0168. So the result was 13.0168, and it takes a lot to type in if you're typing it in by hand like that in all 5 categories. There is an easier way to do this in the calculator, just like there is for either statistical test or confidence interval, which I'll show you that maybe once we conclude the test. So there's my chi-square value, 13.0168, and the reason why I want to hold off on it is because you want to know how to calculate a p-value by hand, or not by hand, but without the calculator function of a statistical goodness of fit test for now. Because sometimes there are questions where they have you do stuff given certain information without actually just going straight to the calculator statistical test application. So we have a chi-square value of 13.0168. So degrees of freedom, by the way, because you're going to want to give degrees of freedom. Number of categories minus 1. In this case, 5 minus 1, 4. So we'll move on to letter D. Is there sufficient evidence? Actually, no, I think I skipped something, didn't I? Letter C is asking for one more thing. They want the p-value also. So I'm going to have to move this and make some room. I don't leave myself much room. So I might have to just write it over here, p-value. And for that, I'm going to go ahead and use a calculator. Degrees of freedom is 4, press OK. My p-value is 0.011, I'll say 2 if I want to round up 4 places after the decimal. So 0.0112, because that 19 rounds up to a 20. So that's what they want. They want the chi-square value here, and I'll box that, which I normally don't box these things in class. I don't care, I'm boxing stuff. So p-value is equal to 0.0112. Letter D. Is there sufficient evidence to conclude that the households in Dove Creek, Montana differ from the rest of the U.S.? At the, okay, so they gave us a significance level, so there's a definite yes or a no. If they didn't give us a significance level, this can go one of 2 different ways depending on what you choose for your alpha level. So in this case, if I chose, or they're forcing me to choose 0.01, and at this case I have to say no. There's not enough evidence for me to conclude that the households in Dove Creek, Montana differ from the rest of the U.S. Now the reason being, p-value is equal to 0.0112, which is greater than alpha 0.01. We should know that if the p-value is greater than alpha, we will fail to reject. So we're going to fail to reject the null hypothesis. So then I'd like to rewrite that in context, in the form of a conclusion. What do we conclude about the null hypothesis? So what was the null hypothesis? First off, null hypothesis was that Dove Creek, Montana fit the distribution, or the distribution for Dove Creek, Montana didn't look very different from the rest of the United States. The alternative is where, yeah, it did differ some way, somehow. So we failed to reject the null. So as far as we can tell, based off of the data, there's no difference between the distribution of household type for the rest of the US and Dove Creek, Montana. So that's what I'm going to write here. So there's not enough evidence. There is not enough evidence to conclude that the distribution of households in Dove Creek, Montana differs from, and I'm going to be lazy here, from that of the rest of the United States. And that's it for this test. So anyway, that's the first problem. We're halfway done with this section. Second problem is where we try this on our own without the aid of the parts A, B, C, and D, just going straight into the four-step procedure that we're used to using for any statistical test. So just to make sure, our null and alternative hypotheses, and I forgot to put HA here, so that's a typo that I gotta fix. H0, the proportion, first proportion is equal to something, the second proportion is equal to something else, dot, dot, dot. The last proportion PM, so if M is the number of categories, then the last proportion is PM. So we might have a different naming scheme like I used over here. We used one that was specific to this particular problem. And it was still kind of confusing. I probably should have gone with 1, 2, 3, 4, and 5. That would have been less confusing. But even then, you can kind of tell what those correspond to. So we have some numbering scheme or naming scheme for those proportions. Make sure you use one. The alternative hypothesis is where at least one of those proportions is different or differs from the hypothesized ones some way, somehow. Step 2, you identify the name of the procedure, and if this is a test for a population having a distribution that fits some other distribution that's already predetermined, this is a goodness of fit test. So chi-square goodness of fit is the name of the test. 2 conditions. Must have a random sample of individuals for that population. And then expected counts must be large enough for us to use a chi-square model. So the minimum number for either of those expected counts is 5. So for any one of those categories, we must have 5 or bigger in each one of those. Step 3, calculate test statistic and the corresponding p-value. Test statistics given here. So chi-square with a little g in subscript, so that's for the goodness of fit test. This might look a little different for other types of chi-square tests. The major formula is about the same, but the space on which we're calculating these values is going to be different. So this is a one-dimensional space for goodness of fit. For a test for homogeneity between populations, or for a test for independence or association between two variables or multiple variables, we're going to have a two-dimensional space, and it's a little bit different for calculating the p-value and calculating degrees of freedom. I think it's really just the degrees of freedom that differs. Step 4, you make a decision, state the conclusion in context. That's where you decide either we reject or we fail to reject the null hypothesis based off of the size of the p-value. And then you rewrite that conclusion, but in context. So look at number 2. USA Today, hybrid car sales rose 81% last year. That's in 2005, so that's not last year. That was 15 years ago. Reported the top 5 states for sales of hybrid cars in 2004 as California, Virginia, Washington, Florida, and Maryland. Now suppose a single random sample of hybrid car sales made in 2004 limited to these 5 states was taken, and that classifying the data by state where the sale took place resulted in the accompanying table. So the observed frequencies, because we had a random sample and it looks like the sample size 406, so we really just need to be able to calculate expected counts. So I think that's what I'm going to do here. I'm going to go ahead and write these as percentages. And then I'm going to go ahead and put expected counts. More on that later, because I know I'm going to have to expand on this table. Or not have to. I'm going to want to. So we'll see how that works. It's going to be a good idea to expand on the table. So this was the data by state. Use a 5% level of significance to test whether the state population proportions hold for hybrid car sales in 2004. So in other words, did it actually matter what state you were in regarding whether or not you were going to buy a hybrid car? Or does that differ by state weighted, like per capita? So is there a major difference per capita? So, or not per capita, but by population. So adjusted for the differences in population, is there a larger probability that you're going to be buying a hybrid car if you live in California versus, let's say, Virginia or something like that? So this is how we would get that done. These are our observed frequencies. And then out of the population, I want to know what those population percentages are. What percentage out of that total population for those 5 states does California make up? So that's where I calculate 35,842,038 divided by a combined total for the 5 states, 72,477,178 people. So if I calculate that, so that's going to be 35,842,038, and that's divided by 72477,178. And that first percentage, and I wrote it as a percentage, should have been a proportion, but not a big deal. 49.45 it looks like. So 49.45% if I write that as a percent. So that's the first percentage. And we can find out the expected count multiplying 49.45% by the total 406. So 406 times 0.4945. And that's 200,767. So I'm going to go ahead and calculate the rest of those in just a bit. So there's the rest of the expected counts and the rest of the percentages, not in that order. So percentages first, then the expected counts. So again, what you're doing is you're multiplying these percentages with the 406 to get these expected counts. So then we'll continue on to the test. So are those way off compared to what was expected? So for California being the largest state, we were expecting 200 out of the 46 or 201 out of the 46, 406 people that were surveyed. And we got 250, which is more than expected. Another one that looks way off, Virginia, 41.9, so 42-ish expected. 56 is higher than expected. If you look at Florida, Florida was under what was expected and quite a bit. So only 33 people, but there was an expected 97 people who should have purchased a hybrid car. So that sort of thing. So are these very different from what was expected? So are the observed counts very different from the expected counts? That's the question we want to answer. So we start off with a hypothesis that we can test. So some sort of testable hypothesis, null hypothesis, H0. And the null hypothesis has to do with the proportions. So we're going to say the proportion for California, California abbreviation CA, and that proportion is 0.4945. The proportion for Virginia, I believe that's VA, 0.1032. And I'm changing these to proportions. The proportion for Washington, which I believe is WA, an abbreviation that is, 0.0856. Where am I getting these? I'm getting these from the percentage column, but changing them back to a proportion. I should have had them as proportions to begin with. For Florida, so the proportion for Florida, and I believe that's FL, that is 0.29, I was going to write another 29999, or 0.2999. And then for Maryland, I believe that's MA, No, that's ML, I believe. I have to double check on that one. But MA, I believe, is Massachusetts. So Maryland is ML? No, MD. I'm way off. Maryland should be MD. So that one is going to be 0.0767. And those are supposed to add up to 1, and I think I checked earlier to see if those add up to 1, but not quite. It's like 0.999 or something like that. So whatever, that's not a big deal. Those are approximate. HA, the alternative hypothesis. So first off, the null hypothesis. Uh, the null hypothesis, if I wanted to expound on that and explain this a little bit more. So this is the idea that the the distribution of hybrid car sales and I'll go ahead and use this term, which is not really a good term to use. It's not a statistical term, but I'll say matches the population distribution. For these 5 states. And the 5 states being California, Virginia, Washington, that's a weird W, Florida, and Maryland. So that's the null hypothesis written 2 ways. One, quantitatively, that's objective, and then qualitatively, which leans more on the side of subjective, depending on how good you are at phrasing the statement. HA. So alternative hypothesis. And what I'm going to do is I'm going to basically negate the qualitative statement. So the statement that I gave up here. So the distribution of hybrid car sales does not match. And I'll put ellipses ... So, and what that means numerically or quantitatively is that one of those, what is that, 1, 2, 3, 4, 5 categories? So again, it's 5 categories, and I've been using 5 a lot. So one of those 5 proportions differs from those stated in the null hypothesis. So those are my hypotheses, which for a chi-square distribution, this is the one that hurts the most. So the part that takes the longest, in my opinion, are the hypotheses and framing them for this test especially. So this is probably the worst test if you're the type that gets annoyed with things like that. This is the one that's the most annoying in my opinion. So we're done with that, at least for this one. The other ones are a little easier. Actually, no, not really. The homogeneity is just as annoying. The test for association is not as bad. So what we do is we name the test. This is going to be a chi-square test for goodness of fit. Or you could have said chi-square goodness of fit test. Would have been good enough. 2 conditions. Do we have a random sample? So I don't know if we do. Yeah, single random sample of hybrid car sales made in 2004. So this is observational data. So what they did was they took data on randomly selected hybrid car sales or car sales. Oh, no, hybrid car sales out of those 5 states. And what they did was they categorized them by the state in which the sales took place. So then we have a random sample then. The exact nature, whether this was something that they looked up online, something they looked up on company records, or if this was actually the result of a survey, I don't really know. All I know is that this is a random sample of sales given. So I was a little bit more specific. It's a random sample of sales in particular. So check mark. Next one, expected counts. And we've already done the math, or at least I did the math. So we've already done the math on the expected counts, and all of those expected counts are large. We need them to be at least 5 all the way around. So all 5 of them need to be at least 5, and they are. So I'm going to go ahead and say all expected counts and I'll put shown in the table above, just in case this were an AP exam and somebody was reading this and I want to make sure that they know that I did the work, and I'll direct them to where that work is at. All expected counts shown in the table above are greater than or equal to 5, check mark. Then what we do is we go ahead and calculate our chi-square statistic, and I'm going to go ahead and show you how to do this on the calculator. So before we do that, let me go ahead and set up the chi-square statistic formula, and we're going to need the expected counts, and not only the expected counts, the observed counts. So we're looking at this and comparing it to this right here. So those are the ones that we're subtracting O minus E squared and then divided by E in that particular order. So chi-square. So we do, let me go ahead and write the formula. Sigma O minus E parentheses squared divided by E. That's the formula. So then what we do is we do that over and over and over. And really, I don't want to write all 5 of them. So we could be this lazy on an AP exam, assuming that this is going to be one of the problems that's on your AP exam. So if something like this showed up, this is the bare minimum. You write the first observed count, 250. The first expected count being compared to that one, 200.767. Was it 676 or 767? I think it's 767, yeah. So sometimes I say one thing and I'm actually reading another, which is kind of weird. So you square that and then you divide this by the expected 200.767. So that's the first fractional quantity that we're going to add in there. And what we do is we go ahead and put a plus sign. I'm going to draw ellipses, dot, 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 another plus sign, and we'll just do the last one. So first and last are good enough. That's the bare minimum. Last one, 33 minus 31.153. This is squared and then divided by the expected 31.153. So then what's expected of us is that we go ahead and plug that into the calculator, divide those and add those, and then we get a final result. We're going to see what we get. Chi-square is equal whatever we get. So for that, I'm going to a calculator. Okay, so here's how we do this in the calculator. Well, we'd want to take a peek ahead first to see what that's going to look like. So a lot of the times you'll forget, and sometimes I tend to forget too, like exactly how to do these. But the chi-square ones, it's a little tough. So I'll get reminded as to exactly what I need if I look at, take a peek into what the test is looking for. So first off, it's under statistical tests, just like you would find the z-test, t-test, 2 sample, 2 proportion, stuff like that. So it's under chi-square, so there's one there, number 7, GOF for goodness of fit. So it's going to ask you for an observed list, and it's going to ask you for an expected list, then degrees of freedom, which that one is what? In this case, it's 5 minus 1, 4. So it's asking for 2 lists, an observed list and an expected list. And for that, we go to a lists and spreadsheets page. So we'll go ahead and add this one, number 4. And I want 2 lists, one for observed counts, one for expected counts. So I'll call these OB and EX respectively. So the first one, OB, is for the observed counts. And the observed counts, I'm looking back at the handout, 250 for California, 56, 34, 33, 33. There should be 5 numbers. Expected counts are the ones that we calculated using the percentages by distribution, 200.767, 41.909, 34.770, 97.389, 31.153. And those are my observed and expected lists. And now we should be good. So I'm going to go back to the calculator page, menu, statistics, number 7, 7 again, observed list, I called it OB, and then EX, and then degrees of freedom. I'm not really sure why they're asking for degrees of freedom. If I was a programmer, I would have programmed it in there to count the number of categories, but whatever. So degrees of freedom is 4. Press OK. And there's our small little table there. So not that much stuff that like we would, or like we're used to seeing for like a 2 proportion z-test or a 2 mean t-test, stuff like that. There's a bunch of stuff that it spits out for you. So here it just gives you a chi-square value, 59.5085. Your p-value is already there, 3.67966. E, negative 12, that just means times 10 to the negative 12, which tells me that the p-value is extremely low or statistically significant. Then it gives you degrees of freedom, and that computational list is probably just something that the programmer put in there for computations between the expected and the observed. What it probably did was calculate the O minus E squared over E thing, but as a list. And that's it. So then we'll go back to the handout. So the calculator gave us 59.5085 for a chi-square value. I don't even have to type in the chi-square value into a chi-square CDF to find out what the p-value was. So I'll just give the p-value as stated from the calculator. Zero. So 3.67, I'll say 80 times 10 to the negative 12, which is very, very small. There's our p-value. So we're almost done with the test. Those are the first 3 steps. The last step. So since, and I could write that down here probably. I have a lot of space, but there's enough space down here too. So since the p-value is extremely small, p-value is small, and I'll go ahead and say less than 1%. I've already written what the p-value is here, so I don't have to write it a second time. And this is good enough for us to reject. These are statistically significant results. Significant if it's lower than the level of significance. So we reject the null hypothesis. What does this mean? There is enough evidence to conclude, and I forgot the word evidence, so there is enough evidence to conclude that the distribution of car sales, hybrid car sales that is, so the distribution of hybrid car sales for these 5 states differs from the population distribution. And I'm going to check to see if there might be a better way to say this, and that's going to depend on the question. So we're testing whether or not the state population proportions hold for hybrid car sales, and I'm not sure if that's a better way to say it compared to the one that I've got. So let's see. No, that's the way they said it, so I could use their wording, but I've already written that, and that's good enough. So I'm going to go ahead and stop here for that particular problem. That's it for problem number 2. And number 2 is the last one on here. So that's it for chi-square goodness of fit tests. So we'll move on to the next handout, and that'll be in the next video.